Dear conference participants, let me welcome you on session number 1, keynote speakers. It's my really great pleasure to introduce the first speaker, who is Mehmet Aksit from the OBB University of Economics and Technology in Ankara. The name of presentation is Designing Sustainable and Scalable Smart City Enterprise System. So, dear Mehmet, floor is yours.
Thank you very much for your invitation, and thank you. It's my honor to be here today. My talk will be indeed about designing sustainable and scalable smart city enterprise systems, and we will especially focus on application to earthquake management. Very short introduction to myself. I have been working at the University of Twente, Netherlands, for many years. So I had my PhD there, and I was also about, let's say, about 10 years, about 20 years, the chair of software engineering department. And after since 2000, begin 2000, I moved to the university in Ankara to set up a smart city research lab. And my background is I have 2 engineering degrees. One is from electrical engineering, and the other one is from computer science. I have got my degrees also from University of Eindhoven in the Netherlands. So after living 47 years abroad or outside Turkey, I am now working in Turkey for a very exciting, challenging project. So as you can see, I have my background is computer science, and at the same time, I had before that an engineering degree in electronics engineering. The table of contents is quite simple. So first we will talk briefly about smart cities and the smart city objectives as we aim at. And then I will give an example case. It's an enterprise for earthquake relief operations. And then I will briefly talk about the approach and give some conclusions. So the nature of automation is the motivation why we do smart city systems. Of course, this is somehow a restricted view, but this is more or less the inspiration what we have. So there is actually a nice book from 1980s, I think, from Xerox Palo Alto Research Center. What does it mean, automation, and why do we do that? From Clarence Ellis and Gary Nutt. Basically, what we want to do is we want to change means. For example, in our case, computation, increase efficiency and effectiveness. Here we define efficiency as more work per unit of money, and effectiveness as we are getting then hopefully closer to our objectives. So we have 2 motivations why we do actually technology like smart cities and so forth. So for example, here type machine is replaced by this word processor. This was quite common in the years 80s. And then of course, we keep on replacing what we have with more computation. In other words, with more automation. We hope that then we increase efficiency, effectiveness. But this is a disruptive process because we cannot go back. Because each time we replace, then we come to a different context, and then the needs of the parts may not be relevant anymore. This model which we have in our mind. So the time, of course, and what I will the changes will be is not always very clear. So when we look at the smart city concept, so it is we are in continuous evolution. In the beginning, of course, we are quite close to the original structure, but then later on, once we keep on replacing what we have, then we come to a context which may not be necessarily compatible with the past. We see also in smart cities that in the beginning it looks very much similar to what we had, but with more automation, computation. But then we may create new opportunities which are quite different than the past. When we look at it from this perspective, we can say that uh, okay, how we position ourselves here as a research organization, the applications we believe that should be developed by companies necessarily because the business context, which actually demand applications, changing and the trends and the expectations, and this is hard to cope. So this is more, let's say, a commercial look. And then, as a research group, we preferably we should focus on infrastructures or generic tools where companies can utilize them and build applications. At the same time, so we are dealing with an information technology infrastructure. So we have, of course, all kind of information technology components, networking, hardware facilities, and so forth. But a very important thing that the AIM infrastructure must be flexible enough to conveniently introduce new technologies and so forth. If you cannot easily adapt and reuse, we cannot be sustainable. So this is actually a very important aspect. The infrastructure must be flexible enough to conveniently introduce new techniques, this is basically our focus. So if we summarize, we can say that smart cities can be defined from many different viewpoints, and therefore there is some, of course, I think confusion in general by different people have different meanings, but basically it's quite normal because you can look at the process from very different meanings, viewpoints, and it's evolutionary steps of automation. Um, we relatively each time we want to increase efficiency and effectiveness, and we do it by replacing existing technology with ICT techniques, and then we keep on replacing and try to improve it with the available technology each time. And it's a disruptive development. That means it doesn't make sense many times to go back because we created a very different need, very different context. And smartness or intelligence is a moving target. It can only be defined relatively. What we may call smart in the past, we may not call smart now. So future cannot be estimated very precisely. So therefore, we need a design flexible infrastructure, and the infrastructure must be designed as enabler, integrator, or harvester. So having said that, let's look at the case of earthquake operations. Especially, we are focusing on earthquake relief operations. So here is, for example, a topology, and then we have here damaged buildings, and we have collapsed building, let's say, and some roads are damaged, and then we have rescue teams, police, ambulance, road repair team, and so forth, possibly distributed to different locations. And the idea is to actually optimally utilize the resources we have. These, and to actually ease or to relieve the pain of the people who are involved in this earthquake. So this is our focus of the smart city kind of applications. It is quite critical for many countries that earthquakes can cause a lot of damage and a lot of lives can be lost. So there is of course a lot of work on that topic. Basically, vehicle routing problem or optimization problems. When we look at the existing relief operations, we see two categories. The first category is the most applied category nowadays, which means this left side means a manual. So basically, you data gather, damage assessment, research, situation assessment, and the need assessment, and then you dispatch, let's say, police, ambulance according to the needs. Still 99% or maybe almost 100% of earthquake management is done in this way. So there is no really, let's say, IoT driven or automatic ways of carrying out relief operation currently. They are, however, semi-automated ones where you still do the data collection, everything, but then you define it as an optimization problem and you try to solve it. The first phase, also data gathering and so forth, is done in general manually, and many times the optimization problem has to be set up by an expert, and this is only possible, for example, if you have a large earthquake that you need to send planes or relief operations and you want to synchronize them in some way. So the current automated earthquake management operations are restricted. So it is partially automation, requires expertise and manual operation. So you put all this information in a machine, and it's a quite computationally intensive task, and you try to optimize some properties. So we want. So the question can be, can we apply smart city systems of today? We think that there is almost no work on earthquake management, and we have I have studied many smart city systems, and from my perspective, they have some serious limitations. One is we want to have household-based data gathering suitable for earthquake management. Uh, this is not what at the level that we want. Standardization and ecosystem infrastructure. What we want to build is an ecosystem infrastructure, like as an example I'm showing here. For example, iPhone ecosystem, which means that there is a standard ecosystem platform where multiple participants, companies can participate on it. We would like to have critical infrastructure, which means that software and hardware infrastructure, fault tolerance, security, and timeliness are there. We would like to have scalability, which means that the system must grow and shrink and so forth. So you need parallelization and special protocols to do scalability. You may have many different examples of applications of earthquake management. So you need easily configuration to different settings. And we would like to have efficient decision support, optimal scheduling of tasks. That means that when you do the relief operations, they can be modeled as tasks, and allocation of tasks to resources. And you need to do a large-scale enterprise control infrastructure to let everything running smoothly. So we think that, especially for earthquake management, current systems are lacking from these perspectives. What we want to do is actually this automatic gathering of household data by using IoT systems, automated damage assessment, semi-automated or semi-automated decision support, automatic generation of tasks for relief operations, and then we see it as an optimization and a scheduling problem. And if you add some future information, you could also do actually simulation for the future and then do assessment and automatic task dispatcher. So how do we approach it to this? We see it as a, of course, large-scale problem-solving problem. So the problem is earthquake management. So we have a design team, and then we have requirements. We divide requirements into problems. So how do we fulfill these requirements? Then we have solution domains, and then we derive solutions from synthesis. So we have a design system, And these problems are including functional and non-functional requirements, including scalability and sustainability. So let's look at these solution domains one by one. The time is too limited to describe all our accomplishment in this. So we gather earthquake data from households. Of course, many people are doing that similar things. The difference here is we are focusing on, of course, households, and we have also earthquake sensors. And then we may also have additional devices. Uh, and then we apply engineering techniques to accomplish what we want. So these are software product lines, like published in this book, systems of systems for scalability, digital ecosystems. This is digital ecosystem. This is systems of system reference, for example. Digital ecosystem means that we build infrastructure where different partners can contribute. So you have to provide the default features of earthquake management, and of course, architectural styles and design patterns to accomplish flexibility and scalability. So we collect information from households. This is rather classic of doing IoT business. But then we have a complex event processing the system where we give meanings to the data streams. So this is a complex event processing system, also used for other purposes, like banks are using that to detect actually fraud. Then we extend the geographic information systems with building information. So this is not really there. So in order to really do earthquake management, you need to combine GIS systems with extended building models, where you can query over models of buildings in a uniform way. So this symbol means actually we are building libraries. So libraries of complex event processing decision systems. And then critical infrastructure, we use fault tolerance techniques and cyber security techniques. And then we, of course, some of them are applicable for platforms, some of them are for more software quality improvement. So we build libraries. And then at the top, once we get information from complex event processing systems, we have a decision support system. And decision support system has its own library. And what decision support system does is to create tasks and resources. Basically, we have many development systems, so it's a continuous development. Experts should define continuous rules. They have to build knowledge bases. And of course, since we are building an ecosystem, so then multiple companies participate on it. So what does the decision system support generate? It generates tasks and resources. So we have library of tasks and resources, and depending on the damage, then we generate task and resource library. It's based on the PhD thesis which I supervised when I was in Netherlands, scheduling system, reusable scheduling systems, and then we get scheduler gives us an optimal order of tasks and resources depending on the damage. And then we dispatch them to the task forces. So once we do that, of course, task forces, we keep on measuring actually the actual performance. We can also build easily a simulator, which means that we put additional data about the future and see what happens if this happens and that happens. And so we are building basically a twin system of the disaster of the city. And then one important problem of twin cities is twin systems, not cities. Twin systems is that your model can be different from the reality. So therefore, we have to continuously measure and see if there is a difference. And if difference, then you apply strategies whether we should reschedule or not. So this is the overall architecture, basically. We gather household data, we do complex event processing systems. They are all different systems with their own knowledge bases and libraries and rules. Experts continuously define them. And then we do task generation and scheduling. I haven't talked about logistics system. We also model logistics system in terms of task and resources, by the way, similarly. And so they are not part of dispatcher, they are part of logistics system, but I haven't shown here. Then we dispatch to task forces So basically, it's a continuous development. Companies share the ecosystem. So the conclusions are management is necessary and can save many lives. We propose an earthquake management system with the following properties. So actually, these properties, well, like I said, all these properties, like I have listed here, are also, I think, suitable to the smart city systems. So our claim is that smart city systems and earthquake management, the super class of all these is large scale management, digital management. So this is, I think, we focus on digital management, and smart city and earthquake management are two applications. Thank you for your time. I don't know if I have time to receive questions, but this was my presentation.
Thank you for a very interesting presentation. I would like to take this opportunity and thank you for our cooperation and for possibilities to work also with your students. I have only short questions. What are the next steps in implementation of your project? Do you plan some pilot application in Turkey, or do you plan new project?
So we had problems with setting up a lab due to the pandemic infection. But we have started building a lab on that. But it's very important that we get support from the government and so forth. So there are a number of companies now forming. So it's a multi-million investment, basically, such a project. But we are talking seriously with the investors. It seems that investors are interested. So I hope we will have, let's say, 2 to 3 companies, and newly company will be established, and investors willing to invest. So we will have a company which will actually will start building for Istanbul, especially is very much. Government is also very much scared of Istanbul earthquake. So it's a serious business. Suddenly we find ourselves in a multi-million business. But of course we will do the research part. Yes. So you may hear that very soon that this will be announced. We are now actually talking with investors. So this will hopefully will be built. But we have now building 3 prototypes. One is a general earthquake simulator, which means this is not our work actually. That it means the earthquake experts are doing that, but this is not really our job. But that's just to simulate the situation. Then we have 2 simulators. One is manual management simulator, and the other one is actually we are building a scheduler, large scale schedulers, to show actually if you do automated management, what is the gain. So we are building now also 3 simulators, especially for the investors, because we are of course asking them in the order of almost millions of dollars. But if you have good idea, the money is not a problem. That's what we think. All right. So we are. It will be a serious business. So we will like to cooperate with people, of course, including yourself and other colleagues. Very welcome to join us.